And so let me remind you, you are looking at this canonical case, canonical exponential families, where you have this parameter theta in RD, rather than this eta parameterization. And this is then called a canonical exponential family. And it's like specified by this T of X and this underlying measure, which is implicit. These densities are with respect to that. And so, for example, we saw that if you take x to be r, T of x to be x and x squared, then if the underlying measure is the Lebesgue measure, then this canonical family would be the two-parameter Gaussian distribution. Okay, the link between these canonical parameters and the original familiar parameters are via this map. Today we'll see a more, let's say, this is natural, but a more natural, let's say, that's not a good word, but the parameterization that's more closely related to the familiar one we'll see today. So what we saw was in the full rank canonical exponential family. So canonical means that parameterization mapping is the identity, and full rank was the technical condition that the interior of now we can call a natural parameter space. So the set of thetas for which this A theta is finite is the set for which we actually have a family, and this is called natural parameter space. So that the family would be full rank if the interior of this natural parameter space is not empty, and the elements of T of X, which is in this case, for example, these the elements of this plus one, the constant one, do not satisfy a linear constraint. So we'll talk about some of the alternative characterization of that today as well. So in a full rank exponential family, so I'm going to write full rank canonical, I'm going to write FRC for short from now on. So full rank canonical, this is like the good family. Full rank canonical exponential families, good things happen. One is that A is convex. This actually holds for any canonical exponential family, I believe. So A is convex on its domain, and the domain is a convex set. So you're going to prove this if you haven't already in your homework problems, and we're going to give it different proofs today. So this gives you a source of convex functions. The proof usually is via the Holder's inequality. The second interesting property in full rank canonical exponential families, the derivatives of A give you information about the moments of the sufficient statistic T. So this result is saying A is C infinity. C infinity means, what does C infinity mean? Let me ask you guys. Derivatives of all order exist and they're continuous. So, but like sort of equivalent because of all order. So they exist on the interior of the domain. And when you take the derivative, so the first derivative, which would be the gradient of A, would give you the mean of T. The second derivative would give you the covariance. The second derivative here is like represented by this Hessian matrix, right? So the elements of this are, hope everyone knows what the gradient is. So the elements are the partial derivatives of A with respect to different elements of theta. This is a matrix, the elements of which are these mixed partial derivatives. So the partial derivative with respect to the second order partial derivative with respect to theta I and theta j would give you the ijth element. So The ijth element would be this. The jth element of the gradient would be that. So this is just saying if you take the partial derivatives of A, you get information about the moments. In particular, the first and second order derivatives give you information about the mean of T and the covariance matrix. So this is the covariance matrix of T. Variance. So hopefully everyone knows what the covariance matrix is, right? So the diagonal elements are the variances of the elements of T. The off diagonals are the pairwise covariance. Right? So this has a lot of information. Yeah, I had it this year, so. Okay, so how do you prove this? The approach is to to calculate the moment generating function. Okay, moment generating function, if you remember, the name moment generating function because the derivatives gives you the moments. So if you calculate it, then you can differentiate it and get the moments. So, so what is the MGF or moment generating function? People remember? It's what I wrote here, right? For a multivariate random variable, basically you take the inner product of u, some generic vector u and t, exponential to that power, and then take the expectation. Okay, usually you'd have a single variable, if you remember from like maybe like t is a random variable. And then you have expectation of e to the like u of t, for example, or something like that. As a function of u, this would be sometimes you usually have like x and then like t of x, like common notation where t is in R. Here we have t is in RD, right? The t of x belongs to RD. We have a d-dimensional family, so this u would be in RD as well. So that's how you form a moment generating function. So this inner product is just u transpose t of x, right? So basically, you form the moment generating function for these univariate projections, if you want. Okay. Sounds good. You plug in, so how do you compute this? You have so this is basically the density t theta of x, right? And this is just a function of x, which is whichever in here. So t of x, remember, is a function of x. This is some g of x, right? So you're computing the expectation of some g of x, capital X. So this would be integral g of little x, t theta of x dx. And dx, it's actually d nu tilde x, but that's the underlying measure. Not important for us. So we're doing something like that. So g of x here is this guy. I'm calling this g of x. Right, that's how you do it. And then the claim is that the next line follows. So why does the next line follow? Yes.
Trying to wrap my head around that, but I think it's the way that we define a, right? Like it was the log of the integral something.
Great. Yes. Okay. Great. Yeah. So if you remember what a was, so if you don't remember, you can always recover what it is. So x, like theta times t minus a theta. That's the density. This has to integrate to 1, right? You remember. And so this means that if I expand, so I can take e to the negative a theta out. This would be integral of e to the theta t. So you want tx, dx, b nu tilde x, and then you take the log and etc. But at this point, this is good enough for us. Okay, so this integral is negative a theta, and you recognize I can take this out, so e to the negative a theta comes out because it's constant, and then the rest is e to the u plus theta t of x, right? So if you can do the calculation in your head, combine these two, get e to the u plus theta inner product with t of x, and then the rest comes out. And so this is exactly this with theta replaced with u plus theta. Okay, so you get e to the au plus theta. Okay, this is, we can write the details, but I'm gonna let you guys either do it in your head or later. It just follows from the definition of things. So the interesting thing is that there's this closed form expression for the moment generating function, and you can see it's in terms of the a theta basically. So that's why it's called cumulant generating function, because the log of this, the log of the MGF is actually cumulant generating function. So if I take the log, basically you can see it's almost like in terms of a, so that's why it's called cumulant generating function. Okay, so that's good. Then I want to take the derivatives and set it equal to 0. So question so far? Yes.
One question. This would be like getting the new measure. It's like the d new tilde.
Yeah.
Is it you like shoving the stuff at the point that's next?
Yeah. I just there was this h of x which I'm putting there, so you can. Yes. Yeah. You can assume that h is 1, for example, and this new tilde is just new. Yeah. But because like I think maybe your book uses h as well and new, so I'm writing it to say that this is like contains both components, but you don't need both really. Yeah, you can just drop the new if you want. Like, sorry, the tilde, not the new. Yeah. Any other questions? Just do the of x for simplicity if that bothers you. No, it doesn't matter. That's like any measure would do, including the Lebesgue measure. Any questions? So this is the technical part. So if theta is in the interior of omega naught is the natural parameter space, then mt is finite. So this moment generating function is finite in the neighborhood of 0. Basically, what we're claiming is like pick theta, and this is by assumption theta is in the. We're going to take the theta to be in the interior, and the interior is non-empty because of the like the full rank assumption. So pick theta in the interior, then mt is going to be finite in a neighborhood of 0. So this is a function of u. So what it means is that if the norm of u is less than some epsilon, then this is going to be finite. So this holds for all the u's that are in the neighborhood of 0. Okay, so this m in the neighborhood of 0 of a certain radius on the inside of this, it's going to be like finite. So why is that? Yes.
Well, a theta is finite.
A theta is finite, yes, because it's in the. Yeah, it's actually because it's in omega naught, but interior is also, it's like inside the omega, yes. But why is this term finite?
So the interior of omega naught.
Yes.
Like, yeah, it's all of which where you have that you can form a ball around a point inside it.
Good. Good, exactly. So by the definition of the interior, if theta is in the interior, there is a little ball around theta, such that it's like completely inside the omega naught, so completely inside the set of parameters for which A is finite. So this u plus theta would be in that ball if u is like in the neighborhood of 0, sufficiently small radius. So then it's going to be finite. So it's exactly like the definition of what the interior is and what this omega naught means. Okay, omega naught means all the parameters for which A is finite. Interior means there's a ball completely inside, and so that's that. Okay, so this is the like E1 assumption, let's say, come in. And whenever you have the moment generating function is finite in a neighborhood of 0, then like interesting things happen, which I'm not going to prove. it's a little bit of measure theory. Dominated convergence theorem implies that this function is going to be like analytic, basically. So like C infinity in the neighborhood of 0, and we can interchange the order of differentiation and integration. That's the really interesting part. So I can differentiate this as a function of u and move the derivative inside the expectation, which I usually have to worry about. But this allows me to do that. Just accept or later try to prove if you want. I think Keener does it in a like a special case. Tries to use dominated convergence theorem, but that would be like a good exercise in measure theory, which we're going to avoid. So I'm going to take the derivative of this. So the derivative of this with respect to the ith component. So u is a d-dimensional vector. By what I just said, I can move it inside. Okay, I can move it inside the expectation. And if I move it inside the expectation, I take the derivative of this function. This would be ti e to the like product, right? So it's exponential. I have to take the derivative of the exponent, which is a linear function. It's just basically just u1 t1 up to ud td, and then so the ith one comes out. The coefficient of the ith one is ti, comes out, and then e to that. So that's how derivatives work. And the other side, if I take the derivative of this, so I have the expression here, right? I'm going to take the expression and then take the derivative of this. If I take the derivative, you can see that partial derivative of this with respect to ui would be what? Would be the gradient of the partial derivative of the numerator, right? AU plus theta minus A theta, and then times itself, which is MTU. And this partial derivative, the second term is 0. So you get partial derivative with respect to ui of A, evaluate the U plus theta times MTU, which is basically what I have here. Okay, it's just a simple derivative. And then at this holds in the neighborhood of 0, in particular, it holds at 0. I set u equal to 0. When you set u equal to 0, this term is going to be 1. So this side turns out to be e theta ti. The other side, when you set it equal to 0, you get the derivative evaluated at theta, right? So you get mt0. mt0 is also like simple. So what is mt0? Mt evaluated at 0. What?
1.
It's always 1, yeah. So I'm going to drop this. This is 1. So we proved what you want. The partial derivative of a with respect to ui is the expectation of the ith coordinate of pi. So this holds for all the coordinates. So basically, we prove that the gradient of a is equal to the expectation of t. So we calculated the MGF, use the property that the interior is not empty to argue that we can interchange differentiation and expectation, and then you differentiate it 2 ways. One, the expression that we calculated, the other one via just moving the differentiation. Inside, you can see this procedure that moves like the differentiation inside gives you the moments. So this is exactly telling you why the MGF, and I take the derivative. So this part is also proving that if I take the derivative of the MGF evaluated at 0, that gives me the expectation of TI. Yeah, that holds in general. So that one we proved. But in this case, this also turns out to be just the derivative of. Okay, once you evaluate at 0, we do the derivative of theta. Yeah, I do UI is just a dummy variable, so it's just taking the derivative with respect to the I coordinate, the value of theta. Okay, good. And then you can do it for the second derivative. You differentiate twice. Again, by the same argument, you can differentiate, do it twice with respect to now uj as an exercise, and you recover that this side would be related to the covariance, the other side would be the second derivative, and you have to argue that you really get the covariance. Okay. Good. Questions? Comments? Okay, so a couple observations. Covariance is always, covariance matrix is always positive semi-definite. This is a property that you can prove very easily. So this is saying that the Hessian of A is positive semi-definite. Okay, because we have shown that the Hessian is the same as the covariance matrix. This guy is always positive semi-definite. So the Hessian of A is always positive semi-definite, and this is a characterization of convexity. So we prove that A is convex via a differential argument. Okay. This we can like verify. Maybe in the homework, maybe there is like a hint of this. If a function is twice differentiable, convexity is equivalent to the Hessian being positive semi-definite. Like the univariate equivalent is that the second derivative is always non-negative. This is like the multivariate version of it. The second point to note, again, this is one of your homework problems, is that the Hessian is going to be singular if and only if the covariance matrix is singular. And so what happens when a covariance matrix is singular? It's like non-invertible, has zero eigenvalue. If you have done the homework problem, probably you would.
Multicollinear.
Yes, so yeah, exactly. So well, the thing to note is like a hint is that the variance of A transpose T for a fixed A, this is going to be A transpose covariance of TA is always true. That also shows why covariance of T is positive semi-definite, because this is always non-negative. That's the definition of positive. So this holds for all. And so if this is singular, it means that there is a non-zero vector A such that this vanishes. So it means that there is a non-zero vector A such that the variance of A transpose T vanishes. So a random variable whose variance is zero is like constant almost surely. So it means there exists a vector A such that A transpose T is almost surely constant. So all the elements of T would lie on it. So if this is zero, this implies, so there exists A such that this is zero. This implies that this is like constant almost surely. So that's saying that there exists like A1 up to AD and some constant C such that A1 T1 up to AD TD plus C is equal to zero, something like that. And so this is saying that T1 up to TD and 1 are linearly dependent almost surely. And so this violates the E2 assumption. Okay, so if E2 holds, then like E2 holds if and only if the covariance of T is non-singular. So this argument, little argument that I did here, which you're going to do in your homework problem more. It's like I just did the homework problem, but you're going to argue this for yourself. Covariance being singular means there exists a direction such that that linear combination of the elements of T is constant. So this is a singular. So T would have a singular distribution, although it's d-dimensional. It's not like scattered. Like if you draw from this distribution, it's not going to be scattered in RD. It's just going to be all of them are lying on a hyperplane in RD. And so that would mean the covariance is singular, and that would mean the A is sort of they call it like the gradient of A would not be regular. So the Hessian would be non-singular. But if you're in a full rank family, because the covariance can't be like that, then the Hessian can't be like that. So Hessian would be full rank. Because the Hessian is the gradient, like the derivative of the gradient. So the gradient would be a regular map. So everything regular, everything nice. Okay, so in a full rank exponential family, there's no singularity, there's no issue. Okay. Sounds good. So convexity follows, and also regularity of the gradient map, let's say. Questions? Okay. So here's a simple example. We have a normal location family. This is the form of the density as a canonical exponential family. And you can identify a theta here, right? So this is a theta. That's my, let's say, h of x. If nu is the Lebesgue measure. The first derivative of a theta is just theta. The second derivative is 1. And so because the t of x here is just x, right? This is t of x. So this is saying that just corroborates what we just proved. Okay. So the expectation of t of x is theta, we know that, and the variance, in this case, just the covariance just reduces to the variance, just 1 by 1. The variance of A is the Hessian. The Hessian is just second derivative here. So this is 1. So this corroborates what we proved. But this gives you a very simple way of calculating the mean and the variance, or the covariance matrix of the sufficient statistic in exponential family. Rather than trying to take the integral or do like a lot of work, basically you differentiate. If you have the log partition function, if you have A, it just reduces to a differentiation problem. You can do it for the Poisson, you can do it for all sort of interesting, even multi-dimensional, like multivariate exponential families. Okay. This is differential identity, so that's one other property. Good. Okay, so let's move on to something else, which is the alternative parameterization of the exponential families in terms of the mean parameter. So we have seen, like there was this generic parameterization eta of theta. From that, we moved to canonical parameterization, which was just theta, right, in RD. So this is an exponential family in canonical form looks like this. I'm using a bit of measure theory notation to just write everything down. So p theta is the distribution. This has density this with respect to nu of x. But the thing is, this theta is the canonical parameter. If I look at the expectation of t of x, we just showed that this is the gradient of A in a 4-rank family. This would in general be a function of theta, right? So that function of theta is a new parameterization. I can parameterize in terms of that parameter. And that's called the mean parameter. Okay, so for example, if you look at the 2-parameter exponential family given by this with respect to Lebesgue measure on R, we know that this is a Gaussian, but that was the form that we got for the density. And let's say the original parameters of the Gaussian, I'm going to write it as m and sigma squared. There was this relation which you can sort of by correspondence with the form of the usual density of the normal, you can figure out. But let's see what the mean parameters are. The mean parameters would be, it would be a 2-dimensional parameter because it would be the expectation of this. So it would just be the expectation of x and expectation of x squared. Okay. The expectation of x is just going to be m, expectation of x squared. The second moment would be m squared plus sigma squared. And so it's more natural, like it's related to the mean and the variance, or just mean and the second moment. It's closer to what you expect if you invert this relation and solve for theta 1 and theta 2 in terms of m and sigma squared. You can plug it in, you get this form for the relation between the mean parameters and the canonical parameters. Okay, from this relation, solve for m and sigma squared and replace m and sigma squared here. So you can see like the relation between m and so there's a theta 1, theta 2. This is mapped to mu1 and mu2 by this mean parameterization. And there is an inverse, as we'll see, that you can go back from the mean parameters to the canonical parameters. And we'll see that there is an inverse going on here, mu inverse. So this gives you another way of parameterizing. So you can reparameterize your parametric model in terms of different parameters. This is often very useful in statistics. So one parameter might be hard to work with or not that interpretable. The other parameter might be very easy to work with. In particular, these mean parameters are very easy to estimate, right? Because they're means of a certain statistic. If I have, let's say, samples x1, x2, xn from this family, IID, each one is a vector in RD, then I can form this T of xi, and then I form the empirical mean, right? Empirical averages approximate the population average. So this is an approximation of this new data. So I don't know the data, that's the job of the statistician to figure out, but data is in one-to-one, we'll see it's one in one-to-one correspondence with mu, as we'll see. So I can instead recover mu, then I can recover theta by inverting that map. In this case, you can see if I recover this mu, I get a system of equations that can solve for theta 1 and theta 2, hopefully. And so because this is a mean parameter, I can just replace it with, like, estimate it with an empirical mean. Okay, and so this gives you some statistical significance why the mean parameter is more interesting or like easier to work with, because it's easier to estimate. This, by the way, is an instance of a method of moments. Okay, so you form the empirical moments, you set it equal to the two moments, like, or the population moments. You solve for theta if you want, but this gives you an estimate of mu without worrying about theta. Questions? Mean parameters are good. At this point, there's not much. Yes.
So where does the use of the second moment come from? You got the new two there.
Because the parameter is two-dimensional. So T of x is, sorry, the sufficient is that the family is two-dimensional. So the mean parameters would be just E of T of x, right? So it would be E of a vector. So it has to have two coordinates. Right. Right, so T of x is just really, this is E theta of T1 of x, E theta TD of x. Okay. Any other questions? This is sort of straightforward. What comes next is not straightforward, but this should be fine, right? Okay. There's like a deeper thing underlying these set of mean parameters. I'm gonna just try to like sketch like the surface, but it's a very interesting property of exponential families. So what would be interesting and mostly have like significance is what are the set of mean parameters that they can realize or recover from this distribution. So you have x and x squared. Can I get any set of mu1 and mu2 out of this family? So is it possible to recover like any set of mu1 and mu2 that I want by an exponential family of this form? Or does mu1 and mu2 have to satisfy certain constraints? Then I have like 1 and minus 1 here. So let me maybe go to the next slide and then sketch the problem a little better. So suppose I give you like a statistic, and I give you this measure, let's say Lebesgue measure on R. And then I want to say, I'm going to look at all the densities. So look at all the distributions on X that have density, let's say, P with respect to the Lebesgue measure. Okay, so I'm going to look at the set of all, like, let's call this P, the set of all things that I can write as P d mu, where P is some density. So for example, a Gaussian distribution has a density with respect to the Lebesgue measure, so that is valid, like a uniform distribution works, and so on. And under such a distribution, so let's say for simplicity, I'm going to write like x distributed like P. Then T of X will have a certain distribution, inherits from this P. And then we're going to look at the expectation of T of X. And that would be like a vector. In our case, would be mu1 and mu2. Okay, and as I vary P among all possible densities, I get different. So this P I can change. This distribution is going to change, and this value is going to change. Okay, I'm going to put a little P here to signify, like, remind you that I'm taking the expectation by assumption that this X has density little P, similar to the things that we were doing. Like, we're looking at the family of probability distributions. The family is pretty big because I'm looking at all distributions that have densities with Lebesgue measure. So I can parameterize by the density. If you want to think about theta here would be this entire density. Okay, so that's my parameter. So if you don't want to think about it as a parameter, it's fine. Just I'm going to vary these densities. So it could be like Gaussian, like uniform, gamma. These are parametric, but any kind of densities, like something like that, like mixture of these, and anything that has a density. So this varies. T of X would inherit a density, like, or a distribution, let's say, not necessarily density. We'll have a distribution because X is a random variable, and this will have a value. The question is that what kind of values can I realize? Yes.
So like in this problem, like the variance is positive. So mu2 minus mu1 squared should be positive.
Great. Okay.
And the mu2 itself is positive.
Mu2 itself is positive. Great. So you got to the gist of it. So I can't realize all possible combinations, right? Because this would be the second moment of this. So basically, this would be the second moment of its distribution, right? And the mu2 would be a second moment, and the second moment and the first moment have a relation, right? Because the variance has to be non-negative for that distribution. mu2 is bigger than or equal to mu1 squared for sure. And also mu2 has to be positive or non-negative. Okay? I can't realize any possible combination because they're moments of a certain distribution. So because they're moments, they're connected by the distribution, they have to satisfy certain constraints. Okay. So that's what we're going to refer to as a set of realizable means for this mapping T. So I specify this T. I specify this Lebesgue measure. Then there's the set of realizable means, which are the set of all. So I'm going to write it as M. It will be the set of all mu's in RD, such that mu is equal to EP T of X for some density T with respect to mu. Okay. And it turns out that in this case, it's not exactly this. I have to correct it a little bit. And I have like something that has 0 variance, still have a density with respect to the Lebesgue measure. So the variance is 0, the random variable is like constant with probability 1. So that distribution is like singular with respect to the Lebesgue measure. So I can't realize, for example, things that have 0 variance. So I have to if I want to define it like this, I have to drop this. So if there is a density, for sure, the second moment is going to be strictly bigger than the first moment squared. Otherwise, if equality holds, equality here means the variance of x is 0, which means that, remember, these are the first and the second moment. So if that equality holds, then x has to have variance 0, which means that things have collapsed into a point. So that doesn't have a density. Similarly, this has to be bigger than 0, because the second moment being 0 means that variance is 0 and the mean is 0. So that's also problematic. So basically, the interior of all possible, so that the set that you said gave is realizable by all possible distributions on x. The interior of this, which is this, is possible by all the densities, which are all distributions that have densities like Lebesgue. Okay, so that is this set. So if this is mu1, this is mu2, the interior of this is what is realized by all densities. And the boundary, if I include the boundary, it would be like everything that's possible by this distribution. Okay. Sounds good. So building towards that result that I want to talk about, but everyone understands this set of realizable means, sort of, right? So so far there's no exponential families. Okay, so this is the set of all possible realizable means by density. So remember, these were ingredients. So if I have this and this, then there is an exponential family, canonical exponential family with these components. But for now, we set it aside, just thought about all possible densities, which is bigger than all possible. So an exponential family is in this class, because the canonical exponential family with that sufficient statistic will have a density respect to that mu. So it would be in this class, but this class is much bigger. Okay. So I'm going to give you the punchline shortly, but I just want to point out the geometric picture first. So this set you can get. It's just a side note for people that are interested in measure theory, maybe. How do I get this set geometrically? So if I put the Lebesgue measure, so if you put the Lebesgue measure on the real line and then put the density on the real line. So for example, I put Gaussian density on the real line, respect to the Lebesgue measure. Densities or measures are basically sort of like distributions of mass. Okay, so I'm going to put this density on P. So how can I visualize the distribution of this T of x? So T of x would be x and then x squared. So if I have like a Gaussian distribution, for example, normal, let's say normal 0, 1, the density of. So what would the distribution of T of x be? In R2.
Moving mass around, right? So it's like the old transformation.
Not that easy. No, it's just I'm not asking for the distribution x squared, right? I'm asking for the distribution x and x squared together. Right. So if you think about it, this has to be on a certain set here. Okay, so it would be on this parabola exactly. So whatever random x I generate from the normals, the second coordinate would be x squared. So it has to lie on this. So it's going to be a singular. So it's going to be a distribution of mass on this parabola. It would be like in visualizing it, it would be like if it's Gaussian, it would be more around here, less around in the tails. But it would be always on this parabola because that's the location of, let's do x and x squared. Okay, so it would be a distribution on this parabola, like concentrated in this parabola, but it's like a distribution of mass, more near zero, less outside. If that's Gaussian, if I change the distribution, like the density, still I'm going to be on this parabola, but I'm going to shift mass around. So maybe like if it's uniform, it would be here 0, 1, but nothing outside. But I mean, you can imagine what this would look like. So this distribution that I get on this is called the push forward of T. So the push forward, the vague measure under the map T. Okay, so this part is like optional. I'm not going to spend too much time on it, but just to mention. So the distribution here would be the push forward, sometimes written as, I believe, I forgot the exact notation, but it's basically the distribution of this random variable. Okay, measure theoretically, it's called the push forward. So it's another distribution on in R2, but it's not singular. So imagine if I had like just if I had a point mass, this wasn't the density. I had a point mass distribution for X, this would be just a single point here. If I have a 2-point distribution, I take like X takes value like 1 and -1 with equal probability. That doesn't have a density, but it's like the distribution. If X takes value plus and -1, I would have this distribution, which is it's like this. Okay, so it's going to be a distribution that's concentrated in these 2 points with equal probability. Okay, and then if you think a little bit about this, if I shift mass around, so what is going to be the mean of this distribution? It's going to be, so if X takes value, this doesn't have a density, but it takes values plus -1 with probability 1/2. You would get X squared is always going to be 1. So you get a distribution which has which takes these values. Okay, so what is the mean of this under this distribution? I'm like moving away from densities for now. Just imagine something like, what is the mean of this? It would be 0, 1, so it would be here. So now if I shift mass around, like if this was like 1/3, this was 2/3, what would I get? The second coordinate is always going to be 1. The first coordinate would be like, the expectation would be. So what would be the expectation of this? 1/3 minus 2/3, which would be, what would it be? -1/3, right? So that would be here, right? So if you shift mass around, if you imagine, as I like change the mass here, so like alpha minus alpha. So what kind of means I can realize for convex combination of these 2 points? I can realize everything in between, right? So this distribution, if I put it here, first you can see it's not like it's like the actual data. So the actual distribution might not be. So yeah, so the mass is here, but the mean can realize anything in between. Okay, so the mass that you put on X moves here, but the mean of it, like in this case, the mean would realize everything in between. So if I change these 2 points to some other points, I would get these other points. And then if I shift mass around between these 2 points, I can realize everything in between. And if you argue like this, if I like put 3-point mass, like X takes three values, right? I can realize anything in the convex hull of these. And if you argue like this way, like n-point mass, I can realize everything. So if you think about it a bit, you realize that the set of means that I can realize by this is really the convex hull of this support of this measure. Okay. So that's the geometric picture. So mathematically, what it is that if I look at the support of this, the support of the push forward is this. This has a convex hull. That convex hull would give me the interior of. Okay, so here's a support. Support is that blue line, and then there's a convex hull. So the convex hull will give me the interior of the set of realizable means. The boundary I can realize, but so that's a nice geometric picture why this happens. Okay. Why we get this relation between the mean and variance. Okay, is it sort of clear? So this is like a side note, but if you care about like geometry, so you can see that set has to be sort of convex. Set of realizable means is convex. Yes.
It's just saying that the interior of the natural parameter space isn't this like just another way of like sort of defining?
No, it doesn't have anything to do with natural parameter space. So this is the mean parameter space. So you're talking about the means. But this was a side note. Okay, so if this wasn't like we could ignore this part. Just wanted to point out that this set is going to be convex, and the way that's realized is by the convex hull of the supportive mu under t. In this case, you know what it is, so like you don't have to worry about just a geometric interpretation. But so far it has nothing to do with the natural parameters. There's no exponential families at this point. Okay. Okay, so the result. Okay, questions. So let's put this geometric idea aside. The result that I wanted to mention is that this set of realizable means that's realized by any, like it's realizable by any possible density. The entire set is realizable by the exponential family that has this sufficient statistic and that mu. So although this is the set that's realizable by every like possible density, if I restrict myself to the class of exponential families, it's still, I get the same realized set of means. So all possible means that I can realize by any density, I can realize by a member of the exponential family with this sufficient statistic and mu. Okay, so we're backing up a little bit from this geometric picture. Forget about the geometric picture. Just back to the definition of the set of realizable means, I can realize everything in there by an exponential family. Okay, it's a significant result. I'm going to mention it, the formal statement. It's significant because the exponential families are a tiny like subset of the set of all possible densities. There are things that look like exponential. They have this particular exponential form. I could come up with very weird kind of distributions, but anything that I can realize with some density, I can realize with this density for some value of theta. Okay, that's the main sort of result that I wanted to mention. Okay, so let me mention this formally. So that's like this slide just basically defines the set of realizable means and that convex hull business up to the interior point basic. So the interiors are the same. This we talked about. And this is the multidimensional version of the Gaussian case. So that's the result. So the result is saying, remember the domain. So let's A be the set of all thetas for which a theta is finite. That's the natural parameter space. In the language of convex analysis, this is called the domain of A. So in a full rank canonical exponential family, there's this technical condition which let's ignore. In a full rank canonical exponential family, the gradient mapping, so the gradient of A, is a one-to-one and onto mapping from the interior of omega to the interior of M. So interior of M here is a set of realizable means, right? The set of all mu's in RD such that this can be written, this is equal to mu for some P, some density P. Respect to nu. So so what it's saying is that the interior of omega, which is the natural parameter space, is mapped in a one-to-one and onto fashion to the interior of M by this mapping, which is the gradient of A. So we know that the gradient of A in an exponential family gives you the expectation of T of X, right? This we showed. The onto part says that basically anything in the realizable means can be achieved by some theta. So there is some theta such that the expectation of T of X for that theta gives me that like particular vector of means. Sorry, the interior of M here. So if there is something that's supposed to map this mapping has to be gradient of A, because gradient of A we have shown it's just the mean, like the gives you the mean of T of X. The significance of this is that this is one-to-one and onto. So there is a bijection. And so there is in particular inverse mapping that maps so there's something that goes in the other direction through the gradient of A, the inverse mapping. Okay, that's the result. People don't look very happy. So basically in this like example, it says, what does it say? It says that any possible set of mean, mu1 and mu2 can be realized by the exponent. The exponential family associated with this statistic is the Gaussian. So this result is saying that if you give me a mean and a variance, there is a Gaussian distribution with this mean and the variance. Any combination of means and variances I can realize by a Gaussian distribution. This might seem very obvious to you, but it's a significant deep result in like probability. So for any set of mean and variances, there is a Gaussian distribution with that mean and variance. Okay, this seems to be obvious to people. It's not obvious. Okay. The fact that there is a Gaussian distribution for any party, so you give me a mean and a variance as long as it's consistent, as long as it satisfies this, right? The variance has to be basically non-negative. Mean can be anything. So give me any non-negative sigma squared and any mu, there is a Gaussian distribution with this variance and mean. So this is saying that there is an exponential family that can realize that set of, the mean parameters would be here like mu squared plus sigma squared and mu, which is almost like variance and mu. It's fine. But any possible realizable mean, any possible mean and sigma squared, I can realize by the corresponding exponential family, which is the Gaussian family. Okay. So now you prove that like a tautology, probably from your perspective, but it's a significance. In general, it's significant, yes.
It does seem very obvious because, like for a Gaussian specifically, it's got that probability density format that you can kind of just plug mean and variance into. So there's like the deeper nature of it from the fact that it can be any function of the means, or like the means can be a giant list, or like.
So if you imagine like the first time, because you have seen the density of the Gaussian, right? So when you come up with this density, originally it's not obvious whether it's like if you come up with this way, it's not obvious. But because you're so familiar with like the form of, so you write down the density, and then you can see for any like sigma squared and mu, this is a density, like integrates to 1. The fact that that happens, it's like happened like many years ago. The first time you observe, so it's not possible. Like you can plug. It could be like I can plug in sigma squared and mu. The thing doesn't integrate to 1, like it's not finite. And also like in higher like more exotic spaces, if I want to define Gaussian processes on like not on RD but on space of functions, can I realize any possible mean and covariance function? Or like more generally, this is a more general result, right?
So it's just something that we've been told since we were this big.
Yes, it's sort of. Yeah, if you have taken like a formal probability course, at some point this came up that there exists for every Gaussian. I remember very vaguely, like maybe like many years ago, I've seen this result at at some point in your career, you would encounter this. Like before you like are familiar with the Gaussian distribution, that there is like the possibility that I can. It's so common now. It's like that doesn't register as a fact that given any mu and sigma squared, there is a density that works, and that happens to be a Gaussian density. There are of course a lot of other, like for any mu and sigma squared, there are other densities that have mu and sigma squared. But the fact that within this exponential family, narrow exponential family, there is one that realizes that it's not. And then you can like imagine adding to this list like x squared and x to the third, then it's not so obvious. Like maybe like it's not going to be like new, maybe change it to like a the on a finite set, and no longer things are obvious. Like put sigmas like sines and cosines and whatever you want. There's no obvious solution there, right? Yeah.
Yeah, I mean, I guess like one more like the parameter space seemed like it could be way bigger potentially than like what the moments of the statistic can give you, but if you're exactly the same size.
No, so the parameters, the set of realizable means is exactly the set of all possible moments that you get. In this case, because they don't have to be moments, but like generalized moments if you want. So this is defined to be all possible moments that you can get by a distribution that has density with respect to nu. But what it is saying is that class of densities cannot realize something that's not realizable by the exponential family with that sufficient statistics. So it's not a very it's significant, but also not very strange, because it's just like, for example, in this case, it's the mean and a variance. It's not too much. But the fact that any combination can be realized by the corresponding exponential family is not an obvious fact. Yes. Okay. Yes.
Yes.
This one.
It's just like for some density p with respect to mu, so the mu is not the big measure, right? It's the big measure times the edge.
In this case, depends on what you want to define. Here, I can like say nu is the Lebesgue measure. Here, okay, so you're saying in this case, it's not the Lebesgue measure because of this edge here. Is that?
So like remember, like so my question actually is like the t actually it lies on a parabola of the R2 space. So its Lebesgue measure is 0, but maybe it's not 0 with respect to the new measure. No,
it's going to be, it's like just if there is this extra factor here, this is not going to change much, because it's still going to be on this, but it's going to be like the distribution is not going to be sort of uniform. Originally, Lebesgue is uniform over the R. Now you have something which is not uniform, but so you're saying what I have here is because of this, it's not necessarily the Lebesgue measure. Here, I think I'm not talking about this case though, but this is fine. I'm talking about this case where like there's no, so if you imagine like it would be like 1 over root 2 pi or something here. Like two parameter, there's no, you really can work with the Lebesgue measure on the line. But even in the univariate parameter case, the fact that this is here is not, in this case, because everything is going to be univariate, there's no this singularity. But this is, let's say, to simplify, this doesn't happen in the R2 case, right? There's no extra factor here. So I'm really working with the Lebesgue measure. Sounds good.
Okay.
Yeah.
So no enforcing a sigma squared cannot be 0 because you are not happy with the here to the empty.
Yeah. So yes. So it's not that not happy, but the boundary cannot be realized by densities with the Lebesgue measure. So if you want to like the correspondence with the Gaussian, there is a Gaussian distribution with 0 density, but it's just sorry, not zero variance, but that will be basically constant random variable. If you want to call it singular Gaussian, it's fine. So the boundary is outside the scope of these results. So like technically you can't achieve it with the exponential family because the exponential family has a density with respect to the Lebesgue measure. But you can achieve it as the limits of these things as they approach the boundary. So you can realize anything in the boundary with the limit of the exponential family, the parameters of the exponential family. Okay. Any other questions? Because I'm not going to get to the next topic, I'm just maybe briefly mention, I'm not going to prove this, but the proof is sort of there. And the proof is really interesting if you're interested in analysis. It's just like a Tour de France of convex and real analysis. You learn a lot about like all of these things if you try to see why the proof is. I'm just going to briefly mention the one-to-one part is not difficult. So I just alluded to basically the condition E2 implies that this the gradient, the Hessian is positive definite. Okay, the Hessian is positive definite means this. If I look at the gradient mapping, this is a multivariate function, right? From RD to RD. This is going to be the Hessian of A would be the derivative of this map. And the Hessian in positive semi-definite means the derivative is 4 rank. So this means that phi is regular. It's called the regular map. And because it's regular map, it's an open mapping, and so it maps the interior to the interior. But the injectivity part comes from the fact that I think you show it in the in one of the homework problems that if the Hessian is non-singular, it has to be positive definite, then the gradient is strictly, like the A is strictly convex and the gradient would be strictly monotone. So this condition is satisfied. It's a monotone operator, and this condition implies that if T is not equal to theta naught, then the gradient can't be equal to like the gradient at 2 point cannot be equal because of this condition. So this is not hard to show that because this is a general property of convex functions. So if the Hessian is positive semi-definite, the gradient, the A is strictly convex and the gradient is strictly monotone, which means this. And I believe something like this you can show. And so this follows from the fact that from E2 basically. So injectivity is easy. The onto part, and then this other part, like this is technical, let's forget about it. The difficulty is like the onto part, the fact that you can realize anything. And in order to show that, what you can do, so we want to show that when I apply the gradient to the interior, so basically this is inside, it's like the other direction. So when you want to show that two are the same, so you show that this is included in that and this is included in the other. So this is, in order to show the onto part, I have to take a mu in the interior of M and then show that there is a theta in the interior of omega such that the gradient of A applied to theta is equal to mu. Okay, so pick anything in the set of realizable means mu. There exists a theta such that the gradient of A theta is equal to mu. The way that this works is we can shift mu without loss of generality so that this mu I can take it to be 0. So you can shift it so that this interior of the M contains 0. And then without loss of generality, I'm going to work with the mean parameter, which is 0. So the problem reduces to showing that if 0 is in the interior, there exists a theta such that the gradient of A at theta is 0. And if you're like, remember optimization, this is saying that like theta is a stationary point of A. So it has something to do with optimization. So if I can show that, for example, A is a convex function, it's going to be a strictly convex function. If I can show that the minimum occurs at the interior of omega, then the gradient has to vanish there. If it occurs at the boundary, it could be that the gradient is non-zero. But whenever a function like differentiable function has a minimum in the interior of its domain, the gradient has to vanish there. Okay, so I can prove it if I can show that A takes its minimum in the interior of the parameter space. And that follows from this kind of argument. A is lower semi-continuous, which we not going to worry about. And then A is coercive and A is essentially smooth. So this result tells you that if a function is coercive, essentially so strictly convex in the interior of its domain, then it attains a unique minimum at some point in the interior of the domain. Okay, so this is a really purely analysis fact, but the facts that we talked about, so A has a lot of interesting properties. So this log partition function is always lower semi-continuous. It's going to be coercive. Coercive means it goes to infinity as theta goes to infinity if the domain allows. And it's convex. It's proper. It means that it's not infinity. And essentially, smooth means that if it's like a if there's a boundary, when it hits the boundary, so the derivative blows up. Derivatives goes to like infinity. That's again a technical condition. In any case, you end up proving that this has all these interesting properties. So it has a unique minimum and the minimum within the interior, and then you're done. Okay. Yeah, so that's basically it. I'm going to next time come back. And so what is the significance of this? Because once you do the MLE, this is another statistical signal. When you try to do MLE, you realize that you have to solve equations like this. So when you try to maximize the likelihood, you're basically minimizing sort of this A. The gradient has to be equal to mu hat, which is the sample mean of this piece. And this is solvable if this mu hat is inside the set of realizable means. So the existence of the MLE in the exponential family reduces to the thing that we discussed, whether the sample mean is inside the set of realizable means. Okay, so I'm going to come back, talk about this a little bit, and move on to the round. Okay, thank you guys. See you next time.